All right, and we're back. Let's talk about the role of the central nervous system in maintaining homeostasis. First of all, what is homeostasis? That is the maintenance of a relatively stable internal environment in the face of ever-changing conditions. So it's maintaining body temperature, whether you go outside on a hot July day or a cold January day. Homeostatic functions include maintaining fluid, electrolyte, and acid-base balance, maintaining blood pressure, maintaining blood glucose and oxygen concentrations, biological rhythms, and body temperature. So the nervous system and the endocrine system are the main systems which are dedicated to maintaining homeostasis. They work together, but each one has its own mechanisms for performing those vital homeostatic regulations. The endocrine system, which you will talk about the first week of A&P2, secretes hormones into the blood, which regulates the functions of other cells. The nervous system sends action potentials, which excites or inhibits target cells. And the actions of the endocrine system are typically slow. They take several hours, maybe even days to have effect, whereas the actions of the nervous system are generally immediate. Two structures of the central nervous system are concerned directly with maintenance of homeostasis. That's the reticular formation, which we talked about in the last video, which controls functions of many internal organs as well as certain aspects of behavior, and the hypothalamus, which is closely associated both anatomically and functionally with the pituitary gland, which reflects their close relationship between those vital systems. The reticular formation and the hypothalamus have many interconnections, which enable them to coordinate many homeostatic functions. Maintenance of vital functions, heart pumping, blood pressure, digestion, is largely controlled by the autonomic nervous system. Again, that's generally going to be abbreviated the ANS, which regulates the function of the body's viscera. And again, viscera are those internal organs like the lungs and the heart and the liver and the kidneys and those things. Although the autonomic nervous system is a component of the peripheral nervous system, it is controlled by components of the central nervous system, mainly the hypothalamus. Although the autonomic nervous system is a component of the peripheral nervous system, again, it's controlled by the central nervous system. The hypothalamus receives its sensory input from the viscera, certain components of the limbic system, and the cerebral cortex. These sensory input allows the hypothalamus to respond to both normal physiological changes and emotional changes, and to adjust the autonomic nervous system output to maintain homeostatic stasis, or homeostasis, thank you. Physiological changes, you eat a candy bar and your blood sugar goes up. You drive by a scene of an accident and see a horrible accident, and that may change your emotional state. Both of those things can be under the control of the hypothalamus. The hypothalamus maintains homeostasis largely by relaying instructions to the nuclei in the reticular formation of the medulla, including the following centers: the vasopressor center, located in the anterolateral medulla. When stimulated by the hypothalamus, the center increases the rate and force of cardiac contraction, causes blood vessels to narrow, which increases blood pressure. Vasopressor center. As the system gets smaller, the pressure is going to increase. Vasodepressor centers are located inferiorly and medially to the vasopressor center. They decrease the rate of heart contractions. They open blood vessels, and all three of these effects decrease the blood pressure. Remember, your blood system is a closed system. If you increase the size of the system, you're going to decrease the pressure within the system. If you decrease the size of the, If you decrease the size of the system, you increase the pressure. If you increase the size, you decrease the pressure. It is an inverse relationship. Many nuclei in the reticular formation also participate in the regulation of digestive processes and control of urination. Respiration is one of the few vital functions not under control of the autonomic nervous system. The rate and depth of breathing are regulated by a group of neurons in the anterior medullary reticular formation. The reticular, several factors influence neuron firing rates. Input from the cerebral cortex, from the limbic system, from the hypothalamus, from your sensory receptors, and certain nuclei in the pons. All of those will play a role in the rate and depth of your breathing. The hypothalamus regulates body temperature, acts as the body's thermostat, the hypothalamus does, creates a set point for normal body temperature, about 37 degrees Celsius or 98.6 Fahrenheit. I do not like this word normal right here. It is actually an average temperature. Some people, my dear mother, for instance, have a low set point. Her temperature is normally somewhere around 98.0 or 97.9. If she has a temperature of 98.6, she's not feeling well. But if you took the temperature of 1,000 people, the average would be right around 98.6 or 37. So a much better word there, and I've lobbied for this for 20 years, it's never going to change, would be an average body temperature, not normal. Input is perceived from temperature-sensitive neurons located in several places, in the skin and areas deeper in the body, and from neurons in the hypothalamus itself. When the body temperature increases above a set point, a negative feedback loop is initiated, whereby certain hypothalamic nuclei induces changes that cool the body. When the body temperature decreases, a different feedback loop is initiated that conserves heat. Both are examples of feedback loop core principle, which we talked about from day one. Fever ensues when the body set point is temporarily set higher than normal. Fever is described as an elevation in body temperature that can accompany a variety of infections and non-infectious conditions. It is caused by chemicals called pyrogens. The prefix pyro means fire. If someone goes around setting fires, they are called a pyromaniac. So these chemicals are secreted by cells of the immune system and by certain bacteria. They can cross the blood-brain barrier and interact with the nuclei of the hypothalamus, the control center, ergo they can change your body temperature. Pyrogens increase hypothalamic set point to a higher temperature. The feedback loop then triggers shivering and muscle aches due to the increased muscle tone and constricts blood vessels serving the skin. Therefore, your skin starts to take on a more sort of pallor, sort of a pale complexion because there's not as much blood in the skin. Therefore, it doesn't have the nice red tone if you are a pale complected person like myself. Treatment is not always necessary, often more important to address the underlying cause. Again, my wife worked in a pediatric clinic for years and years and years. And one of the things that was their biggest issue was a new parent who just had their first child. The child runs a fever of 99 and they're immediately wanting to run them to the clinic. Sometimes it's better just to let the body do what the body is designed to do. Sure, if the temperature gets up to 100, 300, 405, then you do something about it. Antipyretics are used to treat fever. Acetaminophen and aspirin are the over-the-counter. They work by blocking the formation of pyrogens, which permits the hypothalamus to return to its normal set point. So again, the two biggies, over-the-counter, you can get acetaminophen and aspirin. Regulation of feeding, or when do we get hungry and why do we get hungry? Also the job of the hypothalamus. Stimulation of certain hypothalamic nuclei induce hunger and feeding behaviors. These indirectly preserves homeostatic balance of glucose. It's thought to be related to secretion of neurotransmitters called orexins. Orexins are secreted by the hypothalamic neurons during periods of fasting. They appear to induce eating. They also play a role in regulating the sleep-wake cycle. Stimulation of different hypothalamic nuclei seem to inhibit feeding. Mechanisms controlling intake are complex and involve hormones, hypothalamic nuclei, and other regions of the brain. This is one of the reasons that most of those medications for helping diet tend not to work. They may work in the short term, but they don't work in the long term, simply because you've got multiple areas of the brain telling you you're hungry and telling you you're full. One thing about Americans are chronically thirsty. Most Americans cannot differentiate between being thirsty and being hungry. You're sitting there watching a football game on a Sunday afternoon. You go, man, I'm thirsty. And you get up to go fix you a glass of tea. And what do you do while you're in the refrigerator, while you're in the kitchen? You grab a bag of chips or make a sandwich. So we can't differentiate the fact that I'm thirsty from I'm hungry. And most Americans are dehydrated. Sleep. Sleep is reversible and normal suspension of consciousness. It's one of the most fundamental homeostatic processes carried out by humans and most other animals. Information is known pertaining to how we sleep, how sleep is regulated, and the brain activity during sleep, but why most animals sleep is as yet unknown. Physiologically, sleep appears to serve as an energy restoration function and also allows the brain to replenish its glycogen supply. Also seems to pay, and this will probably show up in a moment, but I'm going to throw it out there now just in case it doesn't. Sleep also appears to have a role in memory. Things tend to move from short-term to long-term memory during sleep. It's required for survival. Deprivation can cause imbalances in temperature homeostasis, weight loss, decrease in cognitive abilities, hallucinations, and even death. Most adults only require 7 to 8 hours of sleep. Infants require about 17 hours of sleep. That amount goes down from 17 hours as you age. And most adults, again, 7 to 8 hours. Again, as I told you in class, I don't sleep that much. I sleep, and for my whole entire life, I've slept about 4 to 5 hours a night. Your circadian rhythms, or your biological clock, is the process of how our brain alternates the sleep and wake cycle. We spend a period of the cycle awake and the remainder asleep. The rhythm is controlled by the hypothalamus, which causes changes in the level of wakefulness in response to day and night. Human beings are, by nature, what are referred to as diurnal creatures. We are supposed to be awake during the day. We go to sleep at night. Some early studies were done in this, and if you want to talk about it, come by my office and we'll talk about some of the early studies into why, when factories started being open overnight, the overnight crews were never as good as the daytime crews. And the early thought was they weren't being managed, so they weren't trying as hard, but we now know that there are some differences going on there. Sleep occurs in the following sequence of events. First, the nerves from the eyes signal suprachiasmatic muscles of the hypothalamus nucleus, of the hypothalamus that the light level is decreasing. The SCN stimulates ventrolateral preoptic nuclei of the hypothalamus, which stimulates the pineal gland to secrete melatonin. The ventrolateral preoptic nuclei then decreases the activity within the reticular formation. This decreased activity disconnects the thalamus from the cerebral cortex, which decreases the level of consciousness. Arousal from sleep is mediated by a different group of hypothalamic neurons, which secrete neurotransmitter orexin, and this is all an example of the cell-to-cell communication principle. So signal comes into the eye, tells us the light level's going down, makes a change here, sends here, comes out here, goes up to the sleep centers in the thalamus, and you go to sleep. Brain waves and stages during sleep. Stages of sleep can be monitored using an electroencephalogram or an EEG machine. These measure the electrical activity of the brain using electrodes attached to the skin. if you've ever had a sleep study done, they put one of those, either they put a cap on you or sometimes they just glue the probes. To me, they would probably just glue the probes directly to my head. This traces the electrical activity, which show characteristic patterns. That electrical activity is referred to as brain waves. The waves will differ in height. The height of a wave is referred to as its amplitude, and the speed at which they are generated, the speed is called the frequency. You have low amplitude and high frequency waves which occur when we are awake and engaged in mental activity. These are called beta waves. Then you get ready to go to sleep. You have stages 1 through 3 of sleep, characterized by drowsiness, progressing to moderately deep sleep. Beta waves slow to what are referred to as theta waves, with progressively decreasing frequency and increasing amplitude. So beta waves are low and fast. Theta waves are high and slow. Stage 4 sleep is the deepest stage. This has the characteristic low frequency, high amplitude delta waves. Stage 1 through 4 collectively is known as non-REM sleep. REM stands for rapid eye movement. REM sleep lasts for about 10 to 15 minutes and occurs after stage 4. It's known for the back and forth movement of the eyes. That's why it's referred to as rapid eye movements. Your eyes are literally twitching. If you're watching somebody sleep and you can see that their eyes are closed, but you can see through the movement of their eyelids that their eyes are dancing back and forth, they are in REM sleep. This is the stage where most dreaming occurs. And whether you believe it or not, all human beings dream. Dogs dream, cats dream, horses dream, they all dream. REM waves resemble beta waves, or resemble the beta waves of wakefulness. So here's the sleep waves, here's the awake. You're going into stage 1, producing theta waves, slower than theta waves. You know how to do slow theta. You're into very slow theta. Now you've moved into rapid eye, or the stage 4 delta waves, and then you've moved into rapid eye movement sleep. So this is the progression of about an hour and 15 minutes. And then once you go out of rapid sleep, you will go right back to stage 1. Altered states of consciousness can indicate serious problems with brain functions. Stupor is a diminished level of cortical activity, arousable with strong painful stimuli. This can be caused by infections, mental illnesses, and brain conditions such as tumors. Coma, these are unarousable unconsciousness. You can't shake these people awake. No purposeful responses to any stimuli, even pain. Underlying defect is damage to the reticular activating system or related components. Prohibits the normal arousal of the cerebral cortex. Coma, EEG demonstrates slow, fixed pattern with no observable sleep-wake cycles. The brainstem reflexes remain intact, with certain patients exhibit involuntary movements, may result from head trauma, certain drugs, disturbances in the acid-base homeostasis, various neurological conditions. There was a very famous case, oh gosh, it's probably been 15 or 20 years ago. I believe the lady's name was Terri Shively. But anyway, she was a young woman who fell into a coma. I don't remember why. I just remember the tragedy was her husband wanted to have the life support turned off. Her parents fought against him having the life support turned off because they were saying she was responding to them. What they were seeing was these involuntary movements that will occur in a coma patient. Because they were saying, well, she responds to us. Well, okay, if she's responding to you, why isn't she responding to you all the time? Was the argument. You come in here and you say, hi, Terry, and pat her hand, and she responds. And then the next 10 times you come in and say, hi, she doesn't respond. That's because the brain was undergoing these involuntary movements. Altered consciousness can also indicate serious problems with brain functions, such as a persistent vegetative state. Some patients will move from coma to a condition where they are awake but unaware because of damage to the cerebral cortex. They also lack voluntary movement. Again, this is what is referred to as a persistent vegetative state. The sleep-wake cycles do occur. The brainstem reflexes remain intact, leading to involuntary movements again. The head turns and make grunt-like vocalizations. This is what the young lady I was speaking about previously was doing. Can be interpreted as meaningful but not mediated by the cortex. Thus, they do not imply conscious awareness. Again, they had, this. They attached this young lady to the EEG machine, and they were seeing that there was no brain activity even while she was undergoing these head turning and grunting like vocalizations. There was no brain pattern or brain activity at all. People in altered states of consciousness may occasionally regain consciousness depending on the cause. Brain death, most extreme case of altered consciousness, the EEG shows no activity. The brainstem reflexes are absent. Cerebral blood flow and metabolism are reduced to zero, and consciousness will not be regained. Let's talk about some higher mental functions. Cognition. The collective term for a diverse group of tasks performed by the association areas of the cerebral cortex. Cognitive functions include processing and responding to complex external stimuli, recognizing related stimuli, processing internal stimuli, and planning appropriate responses to all those different stimuli. The cognitive processes are responsible for social and moral behavior, intelligence, thoughts, problem-solving skills, language, and personality. The location of the cognitive function, the parietal association center in your parietal lobe. These are for spatial awareness and attention. They focus on distinct aspects of specific objects and recognize the position of an object in space. Temporal association cortex recognizes stimuli, especially complex stimuli such as faces. The prefrontal cortex, the largest and most complex of the association areas. The majority of cognitive functions that makes up a person's character or personality. Gathers information from association cortices and from other sensory and motor cortices. Integrates that information to create your awareness of self, and allows for planning and execution of behaviors appropriate for given circumstances. Cerebral lateralization, how does it work from one side to the other? The phenomenon in which cognitive functions are unequally represented in right and left hemispheres. That's where you hear people being referred to as being right-brained or left-brained. Represents division of labor between hemispheres to maximize the limited amount of brain space. Following functions appear to be lateralized. The following functions that are on the next slide appear to be lateralized, although it is not an absolute. Emotional functions. The left frontal cortex is more responsible for positive, while the right cortex is for negative. Attention to the right is lateralized to the right parietal cortex. Facial recognition is in the right temporal cortex. Lateral language-related recognition and the ability to identify objects with its proper name are lateralized to the left temporal cortex. Dementia. This is an ongoing field of study in the United States right now. People or patients with dementia exhibit progressive loss of recent memory, degeneration of cognitive functions, and changes in personality. So folks with dementia have poor short-term memory. They may remember what was going on in 1942, but they don't remember what they had for breakfast this morning. Degeneration of cognitive functions. They used to be really great at balancing their checkbook. Now they can't even turn their TV on and off. Changes in personality. They used to be the sweetest, most loving person you would know. that now they've run off most of their family because nobody can stand to be around them. Those are all things that happen with dementia. There is no proven method for prevention of cure of dementia. Some drugs may slow the progression of Alzheimer's in some patients, but do not reverse the changes that already exist. And those drugs are ineffective in other forms of dementia. One of the things that doctors really have to struggle with is patients who come in and they've seen a commercial about an Alzheimer's medication. So they want that medication, but they don't have Alzheimer's. They have some other form of dementia. And again, those drugs, those Alzheimer's drugs, are ineffective with other forms of dementia. Common forms of dementia from most to least, Alzheimer's disease. The body forms what are called neurofibrillary tangles. There are aggregates of proteins. The plaques, which are referred to as senile plaques, form at the conjunction of where the axons and dendrites come together, causing a degeneration of cortical neurons and synaptic connections, which occur throughout the brain, especially numerous in the cortical association areas and the hippocampus. The earliest signs are recent memory loss and forgetfulness, progress to impairment of attention, language skills, critical thinking, visual spatial abilities, and changes in personality. Eventually, motor skills, sensory perception, and long-term memory are affected. Alzheimer's disease is an insidious disease that I hope in my lifetime we can find a cure for, or at least some reasonable treatments. I don't know your individual religious beliefs, but every night when I sit down and say my prayers, I ask God, do whatever you want to do to my body, but let me keep my mind. Vascular dementia is a group of diseases which share common features of disruption in blood parts or blood flow to parts of the brain, particularly cerebral cortex. The signs and symptoms are highly variable because of the range of brain regions affected. Significant overlap with AD. The patients often have both forms, known as mixed dementia. Lewy body dementia and AD, Alzheimer's disease. Lewy body dementia, cytoplasmic inclusions called Lewy bodies form in the neurons of certain cells, causing a fluctuation in cognitive functions, impaired memory formation, hallucinations, delusions, sleep disorders, and the motor features associated with Parkinson's disease. So Lewy body dementia, there is a Parkinson's disease commercial now on where it's a Parkinson's disease medication, and the gentleman he's got a dog sitting next to him, and he sees 4 or 5 dogs, and he says, I didn't know what was going on when I started seeing things. He probably is suffering from Lewy body dementia in addition to his Parkinson's disease. Pick's disease is cerebral formation of frontal and temporal lobe progressively generates, results in severe atrophy due to loss of neurons and excess neuroglia. This one is found usually, it's unusual in that younger population are affected, so it is an unusual type of dementia. Dementia is usually considered to be a disease of the elderly. And I know some of you 19 and 20-year-olds out there think that the 50 to 60 is not considered a younger population. Well, I'm here to tell you, 50 is the new 40, and I've come to the realization that old age is always going to be 20 years older than I am right now. So to be old, I'm 59. You got to be 79 years old. If you ain't 79, you ain't old. Patients deteriorate rapidly. Dramatic personality changes occur. Behavioral problems become common because the prefrontal cortex involved, and all of those things that let you monitor your behavior are no longer functioning. Language is arguably the most important cognitive function found in our brain. The ability to comprehend and produce words through speaking, writing, and or singing, and to assign and recognize symbolic meaning of the word correctly. For those of you who were in class the other day, and I mentioned the guy who got the brain injury and he could suddenly speak a bunch of different languages, and I said he had never spoken them before. I went back and checked on that. And what it was is and I think somebody actually mentioned this, could he just learn them very quickly? And that's what it was. He could hear them once and could repeat them. And if there were, like, he was like watching a French film and it had subtitles, he could read it. And then after watching that movie, could speak French. Of course, he couldn't use words that hadn't been in the movie, but every word that was in the movie he could use. And he could do that with any several different languages. So somebody mentioned that, and I misspoke. I apologize. But yes, he had a brain injury, which allowed him to very quickly learn languages. Broca's areas found in the frontal lobe. These are involved in the production of language, including planning and ordering words with the proper grammar and syntax. The Wernicke areas in the temporal lobe is where we get our understanding of language and linking of words to its correct symbolic meaning, and aphasia is language deficit occurs when either of those two critical areas is damaged. You can have a damaged Broca's area, so you can still understand language and link the words. You may not be able to say them back. Here you can say things, you just don't understand what you're hearing if the Wernicke area were to be damaged. And there's the language cognition areas of the brain, the level of activity of neurons during speech. So the red areas are high, the mediums are low, and the green areas, which I can't even see on this particular slide, are the low areas. I see blue. I guess the green is sort of around the yellow, maybe. One of the things I used to have a poster in my office many years ago that said, and I'll paraphrase here, but always remember to start the motor of your brain before you depress the accelerator of your tongue. In other words, think before you speak. Aphasia is language deficits. Again, the inability, if you have damage in the Broca area, you will have inability to correctly plan and order your grammar and syntax. Words and phrases will be repeated. Grammar, syntax, and structures of identical words will be disordered. Frustrating for patients because language comprehension is intact. They're understanding what you're saying, and they know what they want to say, they just can't say it. And damage to the Wernicke areas is the inability to understand language. You speak fluent with adequate grammar and syntax, but words and meanings are not correctly linked, cannot realize that what they are saying makes no sense. Language comprehension is not intact. Types of memory. This is where it gets fun. Declarative or factual memory, things readily available to the consciousness, could in principle be expressed aloud, hence declarative. Things like your phone number, some quote, or a pathway to cortical or pathways to corticospinal tracts. Non-declarative memory, such as skills or procedural things. These are things that are largely unconscious. How to enter a phone number on a phone, how to move your mouth to speak, how to read a chapter, how to play a saxophone. All of those are non-declarative memory skills. Immediate memory are stored only for a few seconds. They're critical for carrying out normal conversations, reading, and daily tasks. Short-term memory, stored for several minutes, allows you to remember and manipulate information with a general behavior goal in mind. Long-term memory is a more permanent form of storage for days, weeks, or even a lifetime. So short-term is called your working memory. Hopefully, those of you who are attempting to go to nursing school, you are not placing all of this information you are getting from me in your short-term memory. Hopefully, you are putting it in your long-term memory. Process of converting immediate or working into long-term memory involves a process called consolidation. The formation and storage of declarative memory appears to require the hippocampus, which again is a component of the limbic system. Immediate and short-term memories are likely stored in this region as well. Long-term potentiation is a mechanism by which the hippocampal neurons encode long-term declarative memories. seems to involve an increase in synaptic activity between associated neurons. Again, that's that cell-to-cell communication principle. Although the hippocampus is required to form new declarative memories, long-term memories are not stored in this region. They're stored in the cerebral cortex that correlates with their functions. Retrieval of memory seems to be mediated by pathways involving the hippocampus and the prefrontal cortex. Formation and storage of non-declarative memory doesn't rely on the hippocampus memories. Hippocampus. Memories seem to be stored in the cerebral cortex, the cerebellum, and the basal nuclei. So, something comes into your brain, immediate memory. It's going to last for several seconds. It could be immediately forgotten. It could be placed into short-term memory for several minutes, or based on the situation, it could be placed into long-term memory. If it goes into your short-term memory, it may be forgotten in just a few minutes, or it could be brought into the long-term memory. What puts things in long-term memory? Association with other things, the emotion involved, the association with information already in long-term memory. So all of these things will play a role in how quickly something goes into long-term memory. Emotion is a complex combination of three separate phenomena. You have the visceral motor responses. This is blushing or your heart racing, is mediated by the hypothalamus. Somatic, that's visceral. Somatic, you smile, you laugh, you frown, you cry, mediated by the hypothalamus and limbic cortex through reticular formation. And lastly, feelings. Highly subjective, most complex, integrated with sensory and or cognitive stimuli. Now, I stand before you, a 59-year-old product of the 1960s and 1970s. And when I was going to school, I can promise you 1,000% my teachers did not give one flying flip about my feelings. And I think that's kind of sad. I think the pendulum has kind of swung too far. We've gone from not caring about feelings at all, and now we may be caring about feelings in some places and in some instances just a little bit too much. But feelings are important. They're highly subjective. They are the most complex. They are integrated with sensory and or cognitive stimuli. Feeling sad when remembering a lost pet, or feeling tense when reacting to when watching a suspenseful movie. These feelings appear to arise from the amygdala, which receives input from the brainstem, the thalamus, the cerebral cortex, and the basal nuclei. The amygdala then analyzes the emotional significance, creates associations between different stimuli, and projects them to the prefrontal cortex, and then we either cry, we laugh, we frown, whatever we do to accommodate our feelings. All right, I'm going to stop there for today. I will pick up at a later date. It's Friday afternoon where I am. I hope everybody has a great weekend. See you next week.